Okay, everyone, let's begin then. So we were doing iteration. We started this in our last session, and we covered most of the iteration concepts. In fact, all of the iteration concepts. However, as I said yesterday, there will be questions in which you would be expected to sketch graphs. The sketching part, how to sketch different types of graphs, that's what we want to cover today. So there are some functions that you already are supposed to know how to sketch them from paper one. And then there will be some other functions that we will be discussing how to sketch them in today's class. I'll go through all of them, the different kinds of functions that you will need to be able to sketch, and then we'll focus more on the ones that are new for you. So let's begin with this. I'll quickly remind you about what we did in the last session. So we started with this idea that some equations that cannot be solved using algebraic methods, what we do is we use numerical methods to find their solutions. Iteration is one such numerical method. One thing that you would have to do in this topic would be that you would have to prove that a solution of an equation lies between two given values. How do you do that? You first of all have to convert the equation to this form, f of x equal to 0. So you want all terms on one side and have only 0 on the other side. If it's not in this form, you have to convert it to this form. So sometimes you have it like this, for instance. You don't have 0 on one side. So what you do in this case is you take all terms to one side and leave only 0 on the other side like this. Once you're done with that, you just input those two values that are given, for which you have to prove that the solution lies between them. You input one of them once, and then you input the other one. If the sign is changing, if one of them is negative and the other is positive, that means that a solution exists between those two values, right? That's what we discussed yesterday. That's one type of a question that you will see in iteration. Then you would have to be able to use iterative formulas. You'll have to be able to use iterative formulas to solve equations. We learned how to do that. So given an iterative formula, how you can find the solutions to an equation. Sometimes the starting point is given in the question. Sometimes you have to figure it out yourself. So that will generally be your best guess about the solution. Sometimes it's based on a graph. You make your best guess about the solution based on the graph that's given, or based on the graph that you sketch. Or sometimes you prove in one part that the solution lies between two values. For example, if you've proved that a solution lies between 1 and 2, then you can say, okay, if it's anywhere between 1 and 2, your best guess is that it will be somewhere in the middle of 1 and 2. That's 1.5. So you treat 1.5 as the starting value in that case. And then you use this iterative process. We learned how to put this in the calculator. You don't have to do it manually. You just input the initial value in your calculator first, press the equal to button that saves that number in the answer button of your calculator. And then you just input that iterative formula, replacing xn with the answer button on your calculator. And then you just keep pressing the equal to button to get the next iterations. Now, when you do this process, you have to be careful that in your working, your values have to be very accurate. So if they ask you to give each iteration to a certain number of decimal places, you have to make sure that every value is properly rounded off to that number, to that many digits, and the last digit should be properly rounded off. Otherwise, you can lose marks because of that. Then we discussed how to derive an iterative formula given an equation. So if you have an equation like this, how do you derive an iterative formula from this? You make any one of the x terms the subject, right? So if you have this equation, you can either make this x the subject or this x the subject. Then whatever is the x that you have on the left side, you put n plus 1 with that. And on the right side with all the x terms, you put n. And that gives you the iterative formula. In this case, we got two possible iterative formulas like this. And then if you have to find the original equation back from an iterative formula, all you have to do is remove n plus 1 and n, and then simplify that equation. You get to that original equation from which that iterative formula is coming. Okay, that's what we discussed in the last class. And we also looked at a couple of questions after that. In particular, we looked at question number 25 from the worksheet and question number 42 from the worksheet. We would want to do some more practice questions today. But before that, let's try and quickly go over the different graphs that you would have to sketch in this topic. Now, basically, any function that you've done in your syllabus, you should be able to sketch that, okay? You should be able to sketch the graph of that. Now, let's go through the different kinds of functions one by one. First of all, you have linear functions. Linear functions are straight line functions, y equals mx plus c form. How do you sketch straight line functions? You just take 2 points for that. You plot 2 points on a graph, join them with a straight line, and that's your graph. Okay, that's what a graph is going to be. So straight lines are easy to plot. Then quadratic functions are either U-shape or N-shape. U-shape when the coefficient of x squared is positive, N-shape when the coefficient of x squared is negative. C represents the y-intercept of the graph. So when you sketch a quadratic function, you should be able to figure out whether it's a U-shaped graph or an N-shaped graph from the coefficient of x squared. And then you just sketch that by taking some values. So all of these graphs, so that's the general rule that you should remember. All of these graphs, when we sketch them, we will be sketching them by taking some points, plotting them, and then joining them. What you would need to remember from this discussion today, the next 20-25 minutes, is the shape of these graphs. You need to memorize the shapes of these graphs, what a quadratic function looks like, what a cubic function looks like, so that once you remember the shapes, just taking a few points, if you plot them, you would be able to sketch a graph that looks like one of these shapes, right? So if you have any quadratic function, for instance, what you would do would be, you would take some points, you would take some values of x and y, plot those points, and then through those points, either sketch a graph like this or like this. Okay, so you remember the shape that it's either going to be a U shape or an N shape. After taking some points, just draw one of these two shapes. Okay, quadratic functions you've seen before as well. You know how they look like. This is something that might be new for some of you, and that's cubic functions. Cubic functions are functions in which the highest power is 3. We have seen these functions in polynomials before. For a cubic function, the graph is going to be one of these 4 shapes that you see on your screen right now. It's going to be one of these 4 shapes. It's either going to be this or this or this or this. Now, the shapes on the left side, the shapes that you see on the left side, when do you get these shapes? The shapes on the left side, when the coefficient of the x cubed term is positive, you get a graph like this or this, the ones on the left side. Okay. How do you remember that? When the coefficient of x cubed is positive, the graph will be going upwards from left to right. So as you go from left to right, the graph is going upwards roughly, right? Overall, the graph is going upwards like this or this. Now, you do not need to be able to differentiate between these 2 shapes. It could be any one of these 2, but you should be able to remember that it is going to be either this or this. Okay. If the coefficient of x cubed is negative, then it's going to be either this shape or this shape. All right. This d here, the constant term for a cubic function as well, it represents the y-intercept. Now, how would you actually sketch a graph like this? For example, if you have a function like this, x cubed plus 2x minus 3, and you want to sketch this graph for x between minus 3 and plus 3. Let's say you have to sketch this graph for this interval. What you would do would be, you would use the table function on your calculator, and that's what we will use for most functions. We will use the table function on our calculator. If you're not familiar with this, let me go through this process once so that you understand how to do it. Any sketching that you have to do, this table function is going to be very handy. You go to menu, and then you go down, number 9 on this calculator version. I see table here. I select that. Now this is f of x equal to something. In this, I would input this function, x cubed plus 2x minus 3. I have x on this calculator on top right, this button. I can use that. If you have a version that does not have an x button separately, look at the bracket close button. Above the delete button, this bracket close button. Above this bracket close button, you see x written in red. You can access this x by pressing alpha and then the bracket close button, and that will give you x on your screen. Okay. So using any one of these two buttons, now you can just input that function here, x cubed plus 2x minus 3. That's the function that we have. F of x equals x cubed plus 2x minus 3. All right. Press the equal to button. Now this will be handy as well on ClassWorks specifically, that you can make table for two functions at the same time. So sometimes you will see that you would have to sketch two graphs at the same time. What you can do is you can put one of those functions in f of x and then the other function in g of x. All right. Now in this case, we only have f of x. So we skip this, press the equal to button again, and you skip that second functions option. And now in this, since you want to draw the graph from -3 to 3, you say you have to start from -3, input -3 here, and at 3, and the step should be sufficient so that you have enough number of values here. Now, what does that mean? Step basically means the interval, the gap that you want between consecutive values. So if you want a table for x values from -3 to 3, at what interval should you have these values? So for example, if the first value is -3, what should be the next value? Should it be at an interval of 1 or 2? If it's at an interval of 1, the next value would be -2 and then -1 and then 0 and then so on. Okay. If we want values at an interval of 1, we can keep step as 1. So I'll leave it like this for now. And I get this nice table in which I have x values and y values for -3, for x equal to -3, -2, -1, 0, 1, 2, 3. I can plot these values and through those values, make one of these 4 possible shapes. All right. So that's the idea. In order to sketch, you will go to the table function and start. In this case, if you want to sketch from -3 to 3, you would say, let's input -3, end at 3, and step 1 in this case if you want values at an interval of 1. Okay. You plot these values, join them using one of those 4 possible shapes. That's how you would sketch the cubic function. Okay. Ibrahim, if I input f of x here and then press the equal to button, I get g of x as the second function that I can make the table for at the same time. So you will see that sometimes you have to sketch 2 functions at the same time. This calculator version in particular, it allows me to make table for 2 functions at the same time. This is not available in all calculator versions. If you have a different version, you might only see f of x in that. In that case, you can draw 2 tables one by one. So you'll make it for one function once, and then for the second function, you make the table again. Okay. In this ClassWorks version, you can make one single table that will give you values for both functions. We will see a couple of examples on that later on when we do some questions. Okay, so that's how you sketch cubic functions. What you need to remember here is these 4 possible shapes, and the rest calculator will take care of that. Okay, you'll plot some values, draw one of these shapes through those points. Okay, now the next type of function is the reciprocal function. Reciprocal functions are functions in which you have x in the denominator, right? It could be any of these shapes, or you could have x squared in the denominator as well. Any function that has x in the denominator, we call that a reciprocal function. Now, how do you sketch functions like these? There's just one thing that you need to remember, and that is that graphs of these functions, they will be you will be sketching them in multiple parts. So they might have some breaks in the middle somewhere. Why would that be? Because if it's a function 1 over x, for instance, if you input x equal to 0 in this, what happens is the function becomes undefined, so it does not have any value when x is equal to 0. So all or most of such functions, the reciprocal functions, they will become undefined at some value because of having 0 in the denominator. When that happens, the graph will be broken. It'll come in multiple parts. That's all that you need to remember. The rest, you will do it on your calculator. You'll have some interval for which you have to sketch the graph. You will just input the function in your calculator, make a table, plot those values, and through those values, just draw a sketch. Like for example, for if it's 1 over x, the graph is going to look like this. All you need to remember is if you're getting some points here, like this, and then some other points here like this, and they clearly look like two distinct set of points that they are kind of unrelated to each other, don't try to join them like this. Okay, don't join these points. Just remember that the graph can occur in multiple parts like this. Okay, that's all that you need to remember here. Everything else, you can do this on your calculator. You'll just have to plot some values and then just join those points using a curve. The next type of function that you need to be able to sketch are sine, cos, and tan functions. You've done these in paper 1. Again, here as well, the idea is to just remember the shapes. Sine graph, it looks like this. Cos graph looks like this. And the tan graph occurs in multiple parts like this, right? It's like this, and then this, right? Just remember these shapes, that it's going to be one of these shapes. For sine, it could either be this shape, or it could be a reflection of this. Because of some transformation, it might look like this. But the idea is the same. It's going to be a curve that goes like this, a wavy curve like this, okay? That's all that you need to remember. For cos as well, it could either be this, or it might be something like this, if it's a reflection. And similarly for tan. For tan, you need to remember you have asymptotes at some point. Everything else you will do on your calculator. So whatever interval you're given, what you would do would be, you would make a table for that on your calculator, not on your paper. You'll just do it on your calculator, make a table, plot those points, and through those points, make a curve that looks something like this. Okay, now it will not always be sine x function. You might have some transformation of that. For example, 2 sine x minus 3. Again, how do you do that? Just put this on your calculator, plot the points, and get a shape that looks roughly like this. And that's it. That's all that you need to know. Okay. Similarly for cos and tan, these are from paper 1, nothing that you've not done before. You need to revise this if you've forgotten this, but this is part of paper 1. You should know about this. We will see if we can do a couple of examples of this as well when we come to questions. But these are the new graphs for you now. In P3 trigonometry, we did 3 new functions: cosecant, secant, and cot. All right. These are graphs that you have not done in paper 1 before. Let's discuss how to draw the graphs of these functions: cosec, sec, and cot. All right. Now, what is cosecant? Cosecant is the reciprocal of sine. How do you sketch the graph of cosecant function? Let's say you want to sketch this from 0 to 2 pi. Generally, we draw these in radians because most of the functions that you see in iteration, they will have angles in radians. Okay, they will require you to use angles in radians. So let's sketch these graphs in radians. Let's say I want to sketch this from 0 to 2 pi. Now, what I can do for that is I can take some values like this. You will be doing this on your calculator in the exam. You will not make a table like this, but I'm just drawing it the first time for you. So I'm writing down these values in the table so that you understand how to plot them after that. The interval is from 0 to 2 pi. I can start from 0, end at 2 pi. And now let's break this interval down into multiple parts. So you first of all halve it. 2 pi, half of that is pi. Halve it again, that's pi over 2. And then multiply this by 3, that's 3 pi over 2. Now, once you've done some practice, you might find that these points are sufficient for you, and you will be able to understand the shape of the graph from just these points. However, since we're doing it the first time for now, we can break it down further and take some more points. So after 0, we can have pi over 4. And then let me write it like this to make it easier for you to understand. So after pi over 4, we have 2 pi over 4, and then we have 3 pi over 4, and then 4 pi over 4 is pi, and then you have 5 pi over 4, 6 pi over 4, which can be simplified to 3 pi over 2, and then 7 pi over 4. These are the x values that I have. Let's find the corresponding y values for this function. Now, how can I do this on my calculator? Calculator does not have a cosecant function. So on my calculator, I would have to input 1 over sine of x. That's what I would have to input on my calculator. 1 over sine x, put that in the table function. Where do we start? We start at 0 and we end at 2 pi. What about the step? Step is the gap that you want between consecutive values. We are starting from 0, and then we are saying we want the next value to be pi over 4 and then 2 pi over 4. What's the gap between consecutive values? It's pi over 4. So in this case, we can use an interval of pi over 4, gap of pi over 4. Let's put this on our calculator and see what we get from this. Make sure calculator is in radian mode first of all. I've converted it to radians. Now let's input that function there. F of x equals 1 over sine of x, right? That's the function that we have. G of x, skip that for now because we only have one function that we want to sketch in this case. Start, where do we start? We start at 0, end at 2 pi, step pi divided by 4. Now, there's a limitation of the table function, and that is that it cannot show exact values. It will show values in decimals, okay? But you have to show exact values on the x-axis. Now, since you know that you've taken an interval of pi over 4, you would know that the first point would be at 0, and then the next value would be pi over 4, and then 2 pi over 4, and then 3 pi over 4. You would know what the exact values are since you've taken step like this. Every next value will be at a gap of pi over 4. Even if the calculator will be showing the decimal values, you know what you have on the x-axis in exact form as well. This is then 5 pi over 4, 6 pi over 4, 7 pi over 4, and then finally 8 pi over 4 is 2 pi. The table function is going to show you x values in decimals like this. Okay, don't worry about that. You will use exact values using this gap that you have. Now, let's plot the corresponding y values. These are the values that I'm getting. At 0, I'm getting an error. Okay, let's skip that for now. Let's look at the rest of the values. We have 1.4 at pi over 4. Let's mark these points. Let's say this is 1, this is 2, and this is -1, this is -2. At pi over 4, I'm getting 1.4. Now, since you're sketching, we don't have to be very accurate. Just mark a point roughly at 1.4. This is 1.4, okay? At pi over 2 then, 2 pi over 4, the next value is 1. Okay, so we got 1 here. And then at the next value is 1.4. Let's plot that. And the next value after that is an error again. Now, if you remember your tan graphs, what did we used to do when we had an error? Error means the function becomes undefined at that point. When the function becomes undefined, that happens when you have 0 in the denominator. So if you think about it, sine of 0 is 0. That is why when the value of x is 0, cosecant becomes undefined. When a function becomes undefined, that's a general rule that you should remember. Whenever a function becomes undefined, what you do at that point is you make an asymptote. You make a vertical asymptote like this. So at 0, the function is undefined. You make an asymptote like this. Then at pi, again, this function is coming to be undefined. We draw another asymptote at pi. What happens at the asymptote is the graph is either going to go towards positive infinity, it's going to go like this, or it's going to go towards negative infinity on the lower side. Whenever you have an asymptote like this, the graph is either going to go towards positive infinity or towards negative infinity. Now, how do you know if it's going towards positive infinity or negative infinity? Look at the shape that you're getting from the rest of the points. So think about it. This graph is going like this on the right side and like this on the left side. Is it going in the upwards direction or downwards direction? It's going in the upwards direction. That means it is going to go towards infinity on this side, and it will go like this. This is what the graph is going to look like on the left side, and this is what it is going to look like on the right side. That's what the graph is going to be. You can also try inputting a value slightly less than pi. For example, pi is 3.14, right? You can try 3.1 on your calculator, 1 over sine of 3.1. You would see that you would get a large number. That tells you that as you get close to pi, the graph is going to go in the upwards direction like this. So in the table, whenever you see an error, what you do at that point is you make a vertical asymptote. And close to that vertical asymptote, the graph is either going to go to positive infinity or negative infinity. And how would you figure out which side it's going towards? From the points that you do know about, you will look at the shape. Is it going in the upwards direction or in the downward direction? So it's clear from this shape. This is the lowest point on the graph. Then on the right side, it's going up. On the left side as well, it's going up. So at those asymptotes, the graph goes towards infinity. Okay, now let me mark the rest of the points here. So this is the value at pi. We're getting an error. The next value that I see is minus 1.4. Let's plot that. Next value is minus 1.4. That will be here. Then the next value after that is minus 1. That will be here. And the next after that is minus 1.4. That is here. And then at 2 pi, we are again getting an error. That means the function is undefined at this point. Where the function is undefined, we make an asymptote again. It's going to look like this. So at 2 pi as well, we have an asymptote. Now, look at the points that we do know about. Let's join them using a curve. So it's going to look like this on the left side. It's going to look like this on the right side. And then as you get closer to the asymptotes, is the graph going downwards or upwards? It has to go either towards positive infinity or towards negative infinity. In this case, the graph is going downwards. So it is going to look like this on the left side. It's going to go like this. And on the right side, it's going to go like this. That's what the graph of cosecant x looks like from 0 to 2 pi. Okay, now for your reference, I can just write down those values from my calculator here. At 0, it's undefined. At pi over 4, it's 1.4, and then 1, and then 1.4. It's undefined again at pi, and then minus 1.4, minus 1, minus 1.4, and then undefined again at 2 pi. These are the values that we plotted there. And this is what the graph looks like. This is the shape of cosecant x. And now that you've drawn this, you need to remember what it looks like, and that will help you in the exam. Just plotting a few points, you'll be able to figure out this is what it's going to look like. Okay. Remember what the sine graph looks like? Sine graph looks like this. This is the sine graph. Cosecant is reciprocal of that. So where sine is going towards 0, you see, cosecant is going towards infinity, because 1 over 0 point something, 1 over something very small, that's going to be going towards infinity. So when sine is very small, cosecant is very big. When sine is 1, cosecant is also 1, because 1 over 1 is 1. And again, when sine goes towards 0, the graph goes towards infinity, and so on. All right. So that green graph is the sine graph. And you can see they're clearly related like this. They're reciprocals of each other. That's what your cosecant graph looks like. Okay, let's move on. The next graph is secant x. Let's see what the graph of secant x looks like. Okay, let's look at what the secant x graph looks like. Again, we can go from 0 to 2 pi. Let's break it down in the middle like this. We've got pi over 2 in the middle, and then, sorry, pi in the middle. This would be pi over 2, and then 3 pi over 2. Here we have pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Or you can use unsimplified form of this as well, and that's perfectly okay. Let's draw secant x graph now. What's secant x? Secant x is 1 over cos of x. That's secant x, right? 1 over cos x. Looking at the speed that we are going at, we might have to actually spend another session on this, on doing practice questions, because we might not be able to do many today, but let's see. We might have to do another class on doing some more practice on iteration. But let's at least do a couple today, and then we might do another session to do some more practice. Okay, we have these points on the graph like this: pi over 2, 3 pi over 2, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Again, we can have 1 here, we can have 2 here, -1, -2. Just put this on your calculator again. Instead of 1 over sine x now, we need 1 over cos x. Okay, instead of 1 over sine x, now we can put 1 over cos x. All right, 1 over cos x, skip g of x, start at 0, end at 2 pi, and again, an interval of pi over 4. I can just use it as it is. These are the values that I get now. At 0, we have 1. At pi over 4, we have 1.4. At pi over 2, it's undefined. At 3 pi over 4, it's -1.4. And then the next value is -1, -1.4. Error again, so that's undefined. 7 pi over 4 is 1.4. And at 2 pi, we've got 1 again. Let's plot these values. At 0, we've got 1. At pi over 4, it's 1.4, so that will be here, roughly. At pi over 2, it's undefined. What does that mean? We have an asymptote. At pi over 2, we have an asymptote. That will look like this. A vertical asymptote like this. Okay. Then the next value at 3 pi over 4, what's that? At 3 pi over 4, we've got -1.4. So it will be somewhere around here. At pi, we've got -1, then -1.4 again. And then the next value is undefined. So again, we have another asymptote at 3 pi over 2. This is the next asymptote that we have. Okay. And then 7 pi over 4 is 1.4. That would be here. And then at 2 pi, it's 1. These are the points that we have. Okay, now let's start from the left-hand side. This is one point. This is another point. And then we have error. Is the graph going upwards or downwards? It's going upwards. So it is going to go towards positive infinity. So as it gets closer to the asymptote, the graph is going to go up like this. And that's what the shape of the graph looks like. On the right side, it's going to go up like this. Okay, let's go in the middle here. We've got pi and -1, and then this point and this point. Let's join these points. It's going to look like this, and you can see the graph is going downwards on the left and right sides. It'll go towards negative infinity like this. and also go to the to negative infinity like this on the right side. That's what it looks like in the middle. And then in the right side, we've got this point here, this point here. As we go closer to the asymptote, the graph is going upwards, right? So it's going to go like this. That's what the graph of secant x looks like. Okay, and if you were to extend it beyond this interval, you would see it looks like this on the right side, it looks like this on the left side. So it's the same shape that keeps getting repeated, just like it used to be for sine and cos functions. They were cyclic graphs. These graphs are also cyclic. This pattern will keep getting repeated. Yes. So you just have to put values in the calculator. That's all that you've got to do. Okay. And just remember roughly what the shapes are going to look like so that you don't get confused in the exam. You should remember that, okay, roughly this is what the secant graph looks like. It's U's and inverted U's. That's what the shape of the graph looks like roughly. Okay. And then in the graph, it will become easier to sketch something like this in the exam. Okay, so that's secant x. Again, fairly straightforward once you understand how to approach it. Then the next one is cot x. Again, we want to sketch this from 0 to 2 pi. 0 to 2 pi. We've got pi in the middle. Pi over 2. 3 pi over 2. Half pi over 2, that gives you pi over 4. And this is 3 pi over 4. 5 pi over 4. 7 pi over 4. These are the values that we have. Now, let's put this on our calculator. The function is cot x now. What is cot x? Cot x is 1 over tan x. 1 over tan x. However, 1 over tan x is not going to give you correct values on the calculator is not going to give you correct values from 1 over tan x. Okay. The calculator is not going to give you exact values, the correct values for 1 over tan x. Why is that? We'll discuss that in a moment. Instead of 1 over tan x, you should actually be using cos x over sine x here. Cos x over sine x. Okay. Instead of 1 over tan x, for cot, you should be using cos x over sine x to get correct values. Now, let me explain why that is. If you use 1 over tan, for instance, let's see what would happen. 1 over tan. You get these values. At 0, you get undefined. Now, these are not correct values, all of them. Some of them are correct, but some are not correct. If I use 1 over tan, I'm getting undefined, and then 1, and then again undefined, and then minus 1, and then again undefined, and then 1, again undefined, and then minus 1, and again undefined. These are the values that I get when I input 1 over tan x. Okay. However, there's a problem with this. Some of these values are not correct. 1 over tan is the same thing as cos over sine, right? Cot can also be written as cos over sine. If I use cos over sine instead, let's see what I get from that. Instead of 1 over tan, let's use cos over sine. Cos x over sine x. And let's see what we get in this case, cos x over sine x. This gives me slightly different values. So yes, we are still starting from undefined, but then you have 1, and then this value is actually 0. Okay. And then this is undefined, but the next value here, this is again 0. So these values are not errors. These are actually supposed to be zeros. At pi over 2, it is a 0. At 3 pi over 2, it is also a 0. Now, why is it so? Let me correct these values first. Using cos over sine, we get 0 here and we get 0 here. Tan was not giving correct values at these 2 points. But actually, cot is supposed to be 0 here because you can check that using cos over sine. At pi over 2, for instance, you get cos pi over 2 divided by sine pi over 2. What is cos pi over 2? Cos pi over 2 is 0. Sine pi over 2 is 1. So that results in 0. So yes, this should actually be 0. But why is 1 over tan not giving the correct value? Because remember, if you do 1 over tan of pi over 2, what's tan pi over 2? Tan is undefined at pi over 2. Tan function itself is undefined when the value of x is pi over 2. So what happens is when the calculator is evaluating tan pi over 2, it figures out. So when calculator tries to evaluate this whole thing, the way calculator works is it first evaluates this expression tan of pi over 2, and then after that it will try to evaluate this whole fraction. Now when it's evaluating tan of pi over 2, it gets an error at that point. Since it gets an error, it stops the process and it gives you an error as the output. It does not evaluate the whole thing because tan pi over 2 is undefined. It gives you undefined as the final result. It gets stuck in the middle and gives you an error at that point because tan of pi over 2 is undefined. If you use cos over sine, however, cos over sine, this gives you 0. Now, which one of them is more reliable? How do we know that? Remember tan pi over 2, if you think of the graph of tan pi over 2, if you remember that, what used to happen at pi over 2? At pi over 2, the tan graph used to go towards infinity, right? Or negative infinity. So it's either going towards positive infinity or going towards negative infinity. So when you have 1 over infinity, what's that? That's basically 0. 1 over an extremely large number, that approaches 0 basically. So that is why the value of cot there should actually be 0. Calculator gets stuck while evaluating tan of pi over 2, so it does not give you the correct value. Now, that's the logic behind it. But now you need to remember, whenever you're using cot, whenever you're sketching the graph of cot function, always use cos over sine on your calculator instead of 1 over tan. Do not use 1 over tan, use cos over sine on your calculator. And that will give you the correct values. Okay, now that we've got this table from the calculator, let's plot these values quickly. We've got the y-axis here, we've got the x-axis here. We have to sketch this graph from 0 to pi over 2. You start at 0 to 2 pi. Break it down in the middle. Then you have pi over 2 here, 3 pi over 2 here. Break it down further, pi over 2 over 2, that's pi over 4. This is 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, these are the values on the x-axis. On the y-axis, let's have 1 here, let's have -1 here. Let's plot those values. At 0, we've got undefined. What does that mean? We have an asymptote at 0, right? So wherever we have an error, we have an asymptote. At pi over 4, we have 1. At pi over 2, we've got 0. At 3 pi over 4, we have -1. At pi again, we have an error. So we have undefined, we have an asymptote here. At 5 pi over 4, we've got 1 again. At 3 pi over 2, it's 0. And at 7 pi over 4, it's -1 again. At 2 pi, we have an error. So we have another asymptote at 2 pi. This is what the points look like. Now see what's happening. At 0, the function is undefined. So the graph is going to go towards positive infinity. You can see that the graph is going in the upward direction here. So in this region, the graph is going towards positive infinity. Okay, what happens on the right side here? You've got a point here. below the x-axis and the graph is going downwards. So on this side, the graph goes like this. And similarly, in this region as well, on the left side, the graph is going towards positive infinity. On the right side, the graph is going towards negative infinity. This is what the chord graph looks like. And you see, it's very similar to tan. Tan used to look like this, right? Tan was this. No, not this. It was like this. And this was the tan graph roughly, right? It's kind of that tan graph flipped, right? So, and it's going in the other direction instead of that. This is what the chord graph looks like. Okay, very similar to tan, just flipped horizontally. This is the chord graph. Okay, so now you get the idea how to sketch these graphs. Just use the table function on your calculator. Just use the table function on your calculator. Plot these values at the points where you're getting something undefined. You have a vertical asymptote. Okay, and at the close to the vertical asymptote, the graph is either going to go towards positive infinity or towards negative infinity. Okay, that's how you sketch all of these graphs. Let's move on. Cosecant, secant, and chord. Any questions on this before we move on? Any problems in this? Does everyone get this? Does everyone get this? If it's minus secant, it'll flip. Yes, it'll be a horizontal reflection. But again, you don't have to worry about that. Just put that on your calculator. If it's minus secant x on your calculator, instead of putting 1 over cos, you put minus 1 over cos. Let the calculator do the work for you. Don't think about transformation. Just put that same function here, and you get a table for that, and that in this case, right? Plot those values at the point where you have errors. You make asymptotes, and the graph either goes towards positive infinity or negative infinity at those points. All right, let's move on now. So that's the reciprocal trigonometric functions done. Now, the next type of function that you have is the exponential function and the log function. Let's see how they are going to be sketched now. Graphs of e raised to power x and log of x. E raised to power x and log of x. E power x and ln of x. These are the other two functions that you need to be able to sketch. Okay. Now, how do you sketch these graphs? Again, you need to remember the shapes, and then you will just take some points and join those points to get the sketch. All right. Let's start with the exponential function first of all. The exponential function. E raised to power something. E raised to power anything, basically. So you can have some number multiplying outside. You can have some number adding or subtracting outside. All of that is possible. But you have e raised to power something, basically. Let's start with e power x, for instance. Let me write it as a e raised to power anything plus minus b. So a function like this, where you have e raised to power something, and it might have a number multiplying outside or a number adding or subtracting outside. Functions like these, their graphs can be of 4 possible shapes. They can be 4 possible shapes. What are those shapes going to be? They're either going to be like this, or they're going to be like this, or they're going to be like this, or this. These are the 4 possible shapes that you have. Both for the exponential graph and the log graph. Roughly, the shape is going to look like one of these 4 possible shapes. So this is the exponential graph. You can also have a log graph. It might be something like this, log of x, or you could have, for instance, some number multiplying or adding, or some number multiplying or adding or subtracting outside the log function as well. A times ln of bx plus minus c, and then you can have something outside as well. So anything of this form, basically the log function, it also is going to be one of these four possible shapes. Okay, these are the only four possible shapes that you can have for the log graph and the exponential graph. The difference between them is the exponential graph is going to have a horizontal asymptote. It's going to have a horizontal asymptote. That means the graph is going to become flat at some point, like this. It's going to be more flat at some point. Okay. Overall shape is going to look like this, but it'll become flat at some point. The log function, on the other hand, it has a vertical asymptote. Log functions have vertical asymptotes. That means the log graph is going to become kind of vertical at some point, like this or this. Okay, that's the difference between these two graphs. But the overall shape is going to be very similar. Okay. Exponential functions have horizontal asymptotes. Log functions have vertical asymptotes. Okay. Now, how do we sketch these graphs? How exactly do we sketch these graphs? Let's say we have a function that looks like this. Y equals e raised to power something, let's say e raised to power minus 2x plus 4 minus 3. We have a function that looks like this. We want to sketch this graph. Now, how exactly are we going to sketch this graph? There are two things that you need to remember about the exponential function. Two things that you need to remember about the exponential function. One is an important point that you always need to show on the graph. An important point that you always need to show on the graph. What is that important point? It's the point when the power of e equals 0. The important point is going to be when power of the function is equal to 0. That's a point that you always need to show on the graph. Okay, when power is equal to 0. Always take this one point. So in this case, for instance, you put the power equal to 0. That gives you minus 2x plus 4 equal to 0. What value of x do you get from that? X equals 4 over 2. That is 2. X equals 2 is an important point that you need to show on this graph. Okay, that's important. This number here, this is going to be the asymptote of the graph. This is going to be the asymptote of the graph. Since exponential functions have horizontal asymptotes, the asymptote here is going to be, you write that here, horizontal asymptote. This is going to be this number outside. So you can say y equals minus 3. That's the asymptote of this graph. X equals 2 is an important point, and the asymptote is going to be at minus 3. Now, what exactly does that mean? How do we sketch this graph now? Let's have x and y axes like this. We've got y axis here, we've got x axis here. And like we normally do, take some points, take some values of x and the corresponding values of y. This is an important point, x equals 2. You will keep this point in the center, okay? So you have a table of values, let's say x and y. You will keep that important point in the center. What's the important point? When the power is equal to 0. When is power equal to 0? When x value is 2. When x is 2, what's the value of y that you get? Let's figure that out. e raised to power minus 2 into 2 plus 4. Now the power is of course going to be 0. When we do that, minus 3. What's the result that we get from this? 2 and minus 2. That is an important point that we have. We always have to show this on the graph. Let's mark that point. On the y-axis, we've got 2. On the horizontal axis, let's say we've got minus 2 here, and we have plus 2 here, and we have minus 2 here. 2 and minus 2. Where's that point going to be? That point is right here. This is an important point that you always have to show on the graph. Okay. Now we also know an asymptote. The asymptote is at minus 3. Y equals minus 3 is the asymptote. Okay. Y equals minus 3. We have a horizontal asymptote. This is a line that the graph cannot cross. Y equals 3 line, the graph cannot cross this. You have marked an important point here. That's 2 and minus 2. All you have to do now is take a couple of points on either side of this. Take 1 point on the left, 1 point on the right. Generally, that is going to be enough. But if you want to be sure, you can take another point just to understand it better. Let's take, for example, 0 on the left side. X equal to 0. What happens when x is equal to 0? Let's see what value I get from this. When x is 0, I get 51. Okay, so that's a big number. All I care about is, it is, yes, but I'll do that. I'll do that. Yeah, so what was I saying? Yeah, x is 0. When x is 0, the y value that we get is 51. 51 point something. All we understand from that is that it's going to be a large number. It's a big number. Okay. When x is 0, y is a big number. All right, let's take a point on the right side. Let's take 4, for instance. What happens when x is 4? The y value is negative 2.98. Okay. Let's plot the point that you can plot. 4 and negative 2.98. That will be some point here, negative 2.98. 4 and negative 2.98. That's another point that we have. And on the left side at 0, it's 51.6. All that means it's some large number. It's some large number. So that means on the left side, the graph is going to go very steep. It's going to be a very large number on the left side. So now you know this is an asymptote. So on this side, the graph goes like this. It becomes flat like this. On the other side, it increases very sharply and goes like this. This is what the graph of this function looks like. And you see, it is one of these shapes. It looks like this with a horizontal asymptote. Now, why is this an important point? Because this is the point where the graph sharply changes its direction. To the right of this point, the graph is fairly flat. And to the left of this point, it's very steep. So this important point, on one side of this, the graph is going to be flat. And then on the other side of this, the graph is going to be very steep. So that's why it's important to show that point. You show this point, and then using that point, you take 1 point on the left side of that, 1 point on the right side of that, and you know where the asymptote is also going to be. You can draw a graph that looks like this. Okay, that is how we draw graphs of exponential functions. That's how we draw graphs of exponential functions. This is what you remember whenever you have a function that looks like this. E raised to power something plus minus some constant. The important point is always going to be when the power is equal to 0. That's the point that you always need to show. Whatever is in the power, you put that equal to 0. That's an important point. You take 1 point to the left of that, 1 point to the right of that. And the asymptote of this graph is going to be this constant value. That's going to be the horizontal asymptote, y equals plus minus c. That's the horizontal asymptote. Once you have those points, you can sketch a graph using those points. Does this make sense to everyone? It'll be so that's the sad part about it. It's not going to be a lot of marks. Generally, it's just 2-3 marks. Okay. So all they care about is the shape of the graph, the rough shape of the graph. If the shape is correct, that's all that matters. And if there's an asymptote, that should be clear that the graph is not crossing that asymptote. Okay. That's the exponential function. Two things. Important point is when power is equal to 0, asymptote is when the constant is basically the constant that you have outside, y equal to that number, that's the asymptote. All right. Okay, now the other kind of graph is the log function. Let's talk about that next. You can have something like this, for instance, y equals ln of 2x minus 6 plus 3. Let's say I have a function that looks like this. I want to sketch the graph of this function. Now, again, here as well, you need to remember two things. When you're going to have an important point, at what point, so at what value of x you would have to have an important point, and where the asymptote is going to be. Once you know those two things, once you remember those two things, sketching the graph would be easy after that. Okay. What's an important point in this case? For the log function, the part inside, you will be focusing on that. Important point from this is going to be when that inner part is equal to 1. When 2x minus 6 is equal to 1, that's an important point that you have on the graph of the log function. That is when the graph is going to change its direction. It will be flat on one side and it will become very steep on the other side. Okay? Or it will become, it will be steeper on one side and very flat on the other side. Okay? That's an important point that you have in this case. What do you get from this? When you put this equal to 1, the value of x that you get is 3.5 in this case. So now when you're taking values in this case, you would keep 3.5 in the middle. Keep 3.5 in the middle. Take one value to the left of that, one value to the right of that. And that's going to be sufficient as long as you know the asymptote as well. Where is the asymptote going to be of this graph? Asymptote is going to be when this inner part is equal to 0. And remember, for a log graph, the asymptote is vertical. So we'll have a vertical asymptote in this case. And that is when this part inside the log function is equal to 0. What does this give us? This gives us x equal to 3. That is where we are going to have an asymptote. Okay? Because you see, when x becomes 3, the inner part becomes 0, log becomes undefined at that point, right? And any value beyond that, any value to the left of 0, negative values basically, log will be undefined, right? If you have a negative value inside the brackets, it would be undefined. The function would not exist at that point. So that is why we have an asymptote at x equals 3 in this case. What you do now is you make x and y axes like this. You have this y-axis, you've got this x-axis. Let's mark these points. So we have 0 here, let's say, and then maybe we've got 1 here, and then 2, 3, 4. Vertically, we have 1, 2, 3, and so on. Okay, at 3.5, let's see what the y value turns out to be. Again, we just have to mark the points roughly. It doesn't have to be very accurate. One decimal place is going to be enough. Log of 2 into 3.5 minus 6 minus 3. Sorry, plus 3. Right? What does that give us? At 3.5, we've got 3. Right? Because log of 1 is going to be 0. This part becomes 0, and we have 3 outside. This is one important point that we have in this graph. Let's mark this point. At 3.5, we have 3. This is 1 point on this graph. This is something that you will always need to show when the part inside the log is equal to 1. All right. Where is the asymptote now? At x equals 3. That's not because of this 3, by the way. Let me actually change this number so that that is not a confusion. Let's say the number outside was 5. So this 3 is not related to that, right? In that case, this value would actually become 5. So I've changed the function to basically avoid confusion. Let's say the number outside was 5. In that case, when x is 3.5, the y value would be 5. Let me take this point upwards right here. At 3.5, we've got 5. That's an important point that we have on this graph. Okay. At x equals 3, we're going to have an asymptote. So x equals 3, that's a vertical line, right? We draw an asymptote like this at x equals 3. The graph is not going to cross this line. It is going to remain to the right of it. Now what we do is take 1 point on either side of 3.5, take 1 point on the left side of 3.5. Now it becomes undefined at 3. So we'll have to take a value that's greater than 3, right? So let's take, for example, 3.2, 3.1, any value on the left side, just to understand in which direction the graph is going to go on the left side. It's either supposed to go upwards to infinity or to negative infinity, right? One of these two things is going to happen. Take any point on the left side and that will tell you what it would be. If I take 3.2, for instance, that gives me 2.08. All right, so when x is 3.2, y value is 2.1. What does that mean? On the left side here at 3.2, y value is 2.1. So we have a point here. Okay, let's take a point on the right side. I can take 5, for instance. If I take 5, at 5, this value is 4.38. Okay, so I have 5 here. At 5, the value is 4.38. No, that does not sound good. I'm sorry. I have 3 outside here. I changed that function. Okay, that will change both of those values. Okay. On my calculator, I did not update the number outside. It had to change to 5, right? I still have 3 outside on my calc. It still had 3 outside. I'll need to calculate that again. Okay, when x was 3.2, the y value is 4.1. Okay, this is 4.1. That would be roughly around here. Okay, when x is 5 now, the y value is 6.4. You can say that's 6.4 on the right side. At 5, it's 6.4. That will be some point here. And now you can draw that graph. At close to the asymptote, it's going to go like this, right? And on the right side, the graph goes like this. This is what the log graph looks like roughly. Now it looks like a corner here. You can draw something like this. It'll go like this basically. So you see, on the left side of that important point that we marked, it becomes very steep. On the right side, it becomes kind of flat, but not very flat. It keeps going on like this. It does not become, there's no horizontal asymptote here, so the graph will keep going up, although at a very slow speed. Okay, that's what the log graph looks like. Now, what do you need to remember for this? Important point is when the part inside the log is equal to 1, and the asymptote is when the part inside the log is equal to 0. All right. And then you just take 1 point to the left of the important point, 1 point to the right of the important point, and you just join those points like this to get a curve of this shape. Okay. This is the summary for the log graph now. The important point is when the part inside the log is equal to 1, and the vertical asymptote is when the part inside the log is equal to 0. If you just remember these things, the rest will not be that difficult. Yes, it is a bit time taking. Sketching is a bit time taking. I would recommend leave this particular part for the end of the exam so that you don't end up spending a lot of time in the middle. You do not need to show this table on your in your working. You just calculate this from your calculator and just plot the points directly on your graph. Okay, don't show this table. Don't spend time writing it out. Just do this on your calculator and plot the point directly. But do remember these important points and asymptotes. They will help you while sketching these graphs. Otherwise, you'll have to take a lot of points, and that's going to make things difficult. And if you do not show the asymptote correctly, you will also lose marks because of that. Okay, so this is what you need to remember. This is what you need to remember for both of these graphs. Asymptote and the important points. Any questions on this? Any questions on this, anyone? No questions? Okay, what I'll do is I'll just do one question right now, and then we will need to have another class. So what you can do is you can take your time now to do some practice questions, attempt all the assigned questions and possibly more from recent papers. And then we will have a class at some point, maybe next week or maybe the week after that, in which most likely next week we won't leave it for much later. Let's do it next week at some point. We will decide the time. It won't be at the same time, 10:40 to 12, because we will have S1 starting at this time now from Monday onwards. But we will schedule another class in which we will just do practice questions on iteration. So I would recommend that you take this weekend and attempt a lot of questions. And then if you have problems, we will discuss them in that class that we would have. 1 hour class is going to be enough because it's not that difficult. Once you do a few questions, you'll start understanding the question statements. The difficult part is mostly understanding what the question is asking about. Once you understand that thing, then the actual working is mostly not that difficult. Okay. Now, before we end, let's do one quick question. Anyone who has attempted questions already and has any problems, you can let me know one question from the worksheet, and we can do that before we end today. And the rest of the questions, we will do them in the next class that we would have. Any questions from the worksheet? Any specific question from the worksheet? I think I will do one that involves some sketching. So maybe if you can let me know one question that requires us to sketch something. You can just do that one question, then end for today. P3 iteration. Okay. You'll see circular measure questions here as well. Sometimes they end up being a bit tricky. Okay, let me find one where you have to sketch something. Okay, let's try this one. Just one question and then we end for today. Question number 39 from the worksheet. Let's try this. Question 39. It says by sketching suitable graphs, show that the equation secant x equals 3 minus x squared has exactly one root in the interval from 0 to pi over 2. Okay, it's only 2 marks, right? That's a lot of work for 2 marks, but that's what it is when you sketch graphs. Don't spend too much time on this. Be very quick as possible, because otherwise you can end up losing time for the rest of the paper. For that reason, I'd recommend that you leave this part for the very end of the exam. Do not leave the whole question, because the second and third parts here would like be the easiest questions on the paper. Don't skip this. Don't leave this whole question for the end. Just leave the first part. Okay. Second part and third parts of the iteration questions are mostly going to be very straightforward. Do not leave them for the end, because that would mean that you can end up missing out on them if you run out of time. Okay. Always do the second and third parts or fourth part of the iteration question first, and then leave this for the end if they want you to sketch something. Okay, now how do you sketch this graph? Secant x equals 3 minus x squared. It says by sketching suitable graphs. So we have two functions. One is this on the left side, y equals secant x. That's one function that we need to sketch. And on the right side, we have another function, y equals 3 minus x squared. That's another function that we have to sketch. Now, how do we do this? They have given us an interval from 0 to pi over 2. Let's mark these points, 0 and pi over 2. All right, now what we need to do is, in this interval, we need a sufficient number of points to be able to draw graphs for these functions. Let's divide it into two parts. If we divide it into two parts, pi over 2 divided by 2, what's that? That's pi over 4. If I take this as the step, pi over 4, I would just have 3 values, 3 points. This, and this. 3 points are most likely not going to be enough. Let's break it down even further. We're not going to do it manually anyway. The calculator is going to do it for us, right? So we can just take another, we can take a smaller step, divide this into 2 parts again. Pi over 4 divided by 2, what does that give you? Pi over 8. Pi over 8 times 3, that gives us this point. This point is going to be 3 pi over 8. So I've marked these x values here on the x-axis. Now I can just put these two functions on my calculator. Now this is where this class is going to be very helpful, because now I can make a table for both the functions at the same time. How do I do that? Menu, table, make sure your calculator is in gradient mode. The first function is secant x, so I can put that in place of f of x, 1 over cos x, right? Secant is reciprocal of cos, so it will be 1 over cos x. G of x, in this place, in this function, you input the other one, 3 minus x squared, 3 minus x squared. Okay, now start at 0. We have this interval given, right? 0 to pi over 2. We start at 0, end at pi over 2, step pi divided by 8. And that would give us 5 values, right? Starting from 0, pi over 8, this. We'll have 5 points, and then we can easily sketch the graph using those 5 points. Okay. This is the table that I'm getting. Let's start with the secant x function first of all. So I'm calling secant f of x and this g of x. Let's start with f of x first of all. When x is 0, the first value that I'm getting is 1. Let's mark the y-axis first by looking at the points and seeing what's the highest point on the graph in this interval and what's the lowest point. So maximum it's going is up to around 3, right? 2.8 is the maximum number that I can see for both of these functions, 2.8. So vertically, I can have a scale like this. I can say this is 1, this is 2, this is 3. If I had bigger numbers, I would have had to use a bigger scale on the y-axis. Otherwise, I would not be able to show those points. Okay, so I have 1, 2, 3 like this. Now let's plot these points. When x is 0, y is 1. I'm starting with f of x first of all. When x is 0, y is 1. Then the next value is 1.08. So slightly above that. Okay. The next value is 1.4. Okay, slightly above that. 2.6. Again, it's going slightly up again. The next is an error. Error means we have an asymptote at 𝗲𝗽/2. This is what the graph of secant x looks like now. You can see the shape of the graph. It's going to go upwards like this. At the asymptote, it's going to go towards infinity. That's what the graph of secant x looks like. Okay, that's the function on the left side here, secant x. What about the other one, the quadratic function? It's minus x squared, right? It's supposed to be an n-shaped graph. The complete graph would be n-shaped, but this will just be some part of that. At 0, we've got 3. Okay, so that's the starting point. At 0, we have 3. Then the next value is 2.84, so it's going slightly below here. 2.38, so 2.4. And then 1.6 is somewhere around here. And then 0.5, that's going around here. You just draw a shape like this through these points, something like this. Okay, that's the quadratic function. It's only some part of that graph. Now on the left side somewhere, it would go like this, right? But that's not what we want. We only wanted the graph from 0 to 𝗲/2. So we would just show that part. These are the two graphs that we had to sketch. We would label them because you would not be using different colors in your exam. It would just be using a pencil, right? You would clearly label that this is y equals secant x and the other graph is y equals 3 minus x squared. Now, this is not going to earn you 2 marks just yet. So when you sketch these two graphs, now they're saying, show that it has exactly one root. How do we show that? You have to clearly point that out. Where is that one root? This is one root. You will say, pointing this out, this is exactly one root. Or you write in words that there's only one point of intersection. That is why there is only one root. You have to clearly tell the examiner that you understand that the point of intersection gives you the solution of this equation. Since there's only one point of intersection, that means there's only one root in this interval. That's what you would show here. And that gets you those 2 marks. Okay. Now the second part says, show that if a sequence of values given by this iterative formula converges, then it converges to a root of the equation in part 1. We did a very similar question in the last class, and I told you that this kind of statement, they repeat in a lot of questions. If this iterative formula gives you a solution, they are saying, show that that solution is the same as the solution that you would get for this equation. So this iterative formula, you have to show it corresponds to the equation in the first part. That's what you have to show, that these two things, they correspond to each other. How do we do that? Let's write down the equation that we have. Secant x equal to 3 minus x squared. The iterative formula, that's xn plus 1 equals cos inverse of 1 minus 3 minus xn squared. We either start from this equation and show that it can be converted to this form, or start from the iterative formula and show that this can be converted to this form. We can go in either direction. Let's start from this iterative formula. That's mostly easier. Remove n plus 1 and n from that. That leaves you with x equals cos inverse of 1 over 3 minus x squared. Take cos inverse to the other side. That becomes cos of x equal to 1 over 3 minus x squared. Take reciprocal on both sides. Reciprocal of cos, what's that? That is secant. Reciprocal of this number, that is 3 minus x squared. This corresponds to that equation. That means whatever solution you get from this iterative formula, it will be the same as the solution for this equation. So that's what you need to show. You need to show that that iterative formula and the equation, they correspond to each other. This iterative formula is a formula for this particular equation. Okay, that's the second part. And then in the third part, they just want you to use this iterative formula with an initial value of 1 to determine the root in this interval, correct to 2 decimal places, showing the result of each iteration. Now, this is interesting. They have not told you how many decimal places to use in each iteration. They have just told you that you want the final answer correct to 2 decimal places. Final answer should be correct to 2 decimal places. What about the iterations? What should be the level of accuracy that we use for each iteration? What should be the level of accuracy that we use for each iteration? We discussed this yesterday. The iterations have to be 2 decimal places more accurate than the final answer. Okay, 2 decimal places more accurate than the final answer. Whatever is the final level of accuracy that you want, the iterations have to be 2 decimal places more accurate than that. So the final answer has to be 2 decimal places. That means your iterations have to be correct to 4 decimal places. Okay, iterations have to be correct to 4 decimal places. Starting value is 1. Let's do that. The iterative formula is this: xn plus 1 equals cos inverse of 1 over 3 minus xn squared. Starting point is 1. Make sure your calculator is in radian mode first of all, and then input 1. That saves 1 in the answer button. Then you do cos inverse of 1 divided by 3 minus answer squared, bracket closed. So you just replace xn with answer. See what you get from that. Pi over 3. Write that to 4 decimal places. 1.04719. That means 0472. x3. What would that be? 1.0176. x4. 1.0367. x5. 1.0246. x6. 1.03237. That means 4. x7. 1.02744. So we can say 4. x8. 1.03059. We can say that's 06. Okay, now all the decimals are not becoming stable, but what do we want at the end? We want our final answer to 2 decimal places. If you have gotten to like x7, x8, and you've done like 8, 9 iterations, and it's still not getting stable to all decimal places, you would stop and see, okay, the final answer that you want is supposed to be correct to 2 decimal places. Think about it. This is 1.03, correct to 2 decimal places. This is also 1.03. This is also 1.03. Once you have 3 consecutive iterations that are giving you the same result, it's okay to stop at this point, because now the final answer is not going to change. It is going to keep rounding off to 1.03. So it's become stable. The final answer that you want to 2 decimal places, it's fairly stable now. You can try one more if you want. And that gives you 1.0285. So that will be 6. 0 to 8, 6. This also rounds off to 1.03. You have a number of iterations now that are rounding off to 1.03. You can say the final answer, therefore, is going to be 1.03. Have they named this value anything, alpha or something? No. Okay, so we'll just say the final answer, therefore, is x equals 1.03, and that's your final result. Don't write any more iterations than this, but to be sure about it yourself, you can keep pressing the equal to button on a calculator now, just to see that it does in fact get stable at 1.03 and that value is correct. Just keep pressing the equal to button again. So it becomes stable at this value, 1.0293. That does round off to 1.03. So that's your final result. That's the value that we were looking for. That's part 3 of this. Okay, I hope that makes sense. Now, please make sure to attempt more questions from the worksheet. It is important. You will find some questions that are going to be a bit more confusing. Make sure that you attempt them. Then you can either post them on the WhatsApp group, or you can ask them and ask about them in the next class that we would have. One last class in which we will discuss some iteration questions. And if any of you has any other questions from any other topic in that class as well, we might be able to discuss those as well. But that class, we will have to decide some other time slot for that, because we will be starting S1 in this time slot from Monday onward, inshallah. All right, that's it for today. I'll see you again in the next class then. If you have any quick questions, you can let me know. Otherwise, I'll see you again on Monday, inshallah. Any questions, anyone? Okay, question 2, part 1. You just want me to give you a hint on this? All right, I'll do that quickly and then we end. Question 2, part 1. Okay, now this is circular measure, right? This is alpha radians. Okay, anyone who wants to leave, you are free to leave. You can. I'll be posting the recording right after the class as well, inshallah. But I'll just give Ibrahim a hint about this question quickly, and then I'm ending this. If you want to leave, because it's quite late now, you are free to leave. I'll just explain this then, and then we end the class as well. Okay, so we have this sector OAB, with center O and radius R. The angle AOB is alpha radians, where alpha is between 0 and pi/2. It's an acute angle. OA is perpendicular to BN. Area of triangle ONB. So that's the point. That's the part that's going to tell you how to make an equation. Area of triangle ONB is half the area of the sector OAB. So we can use this thing to make an equation now. Area of this triangle and area of this part, they're equal to each other. Okay. One idea that we can use here is we can say if we multiply the area of the triangle by 2, we would get the area of the sector, right? If these two areas, if this area is A and this is also A, then the total area is 2A. So the area of the triangle multiplied by 2 will be the area of the whole sector. So I can do something like this. I can say area of sector, that would equal 2 times the area of the triangle O and B. All right. What's the area of sector? Half r square theta. Half r square theta. And the angle is alpha here, so we can say half r square alpha. That should equal 2 times the area of O and B. It's a right angle triangle. We do not have the base of the triangle or the height of the triangle. We can use half AB sine C if we want. If this is R and this is alpha, we can use trigonometry to find, for instance, this length ON. This would be base, this would be hypotenuse. What's the ratio between base and hypotenuse? It's cos. So we can say cos of alpha, that equals ON over R. So ON equals R cos alpha. This side is R cos alpha. We have two sides and the angle between them. We can use the formula half AB sine C for the area of the triangle, half into one side, into the other side, into the sine of the angle between them, which is sine alpha. That's the area of the triangle. You rearrange this and you would get that result somehow. Let me simplify this for you first. Half R squared alpha equals 2 and 2, they get cancelled, and we have R squared into sine alpha into cos of alpha. R squared and R squared, they get cancelled. We have alpha equals 2 sine alpha cos alpha. Does that remind you of something? 2 sine alpha cos alpha. That's the double angle identity for sine, right? This becomes sine of 2 alpha. So we have alpha equal to sine of 2 alpha. This is exactly the same equation. Since alpha equals sine 2 alpha, if we were to replace x with alpha here, this is correct. So alpha does satisfy this equation. Okay? Make sense? All right, now let's actually end this class here. And for the next class now, one last session on paper 3. You will be doing more questions on iteration and letting me know if there are any specific problems. All right, I'll see you again on Monday when we start our next paper, which is S1 or M1, whichever paper you're doing. I'll have an introductory class tomorrow, by the way, for those of you who want to attend it. That's mostly for new students who have not taken paper 1 and paper 3. I'll just introduce them to the different tools that we use in our classes, and then we start our first topic on Monday, inshallah. So the topic will start on Monday. Okay, the first topic for M1 or S1. All right, Allah Hafiz everyone. I'll see you again in the next session.